So, so we have completed some of the very important topics like Coulomb's law and Gauss law, and as well as the potential gradient. All these things, if you see that, they will be either discussing about continuous distribution or point distribution of charges. And by the way, we will calculate the electric field at a particular point or potential at a particular point. And so these all things we are actually calculating for various applications. In the near future, you are going to study transmission line theory. That is the last 2 units you will see there. And as well as in the future, we will see other electromagnetic systems like antenna system, as well as the capacitors, inductors, even transistors, and then diodes. Everywhere, actually, you will see that this so-called field theory will come into the picture. And for that, the electrostatics is very, very important. In the future, sometime we'll be having some free slots. I will teach you how to solve these kind of equations for complicated transistors and how easily we can solve the problems all the way using some simple numerical methods. And if possible, I will teach some of the electromagnetic simulation tools so that you can easily develop so many things. For instance, Apple recently asked for an antenna engineer, and they want three things to be understood: the electromagnetic field theory, antenna theory, and so-called microwave engineering, which comes under the transmission line theory. So these three theories, if you know, then you can easily get a job at Apple, and you know that how much salary, all these things. So you could always keep this eye on this concepts of electromagnetic field theory and their applications. And so far now we have completed up to Poisson's and Laplace equations and some of the applications like capacitance out of that. And one of the special case parallel plate capacitor we have seen. So we will see, we will explore the other alternate methods which are useful to solve the electrostatic problems. So Coulomb's law describe about the field distribution at any particular point with respect to a source charge. And when we bring another charge nearby, then this force will be acting upon that can be calculated. So this both the methods are very much acceptable. And later we have calculated for different charge distribution. So this three things what you have learned in the beginning of the electrostatics is describing the problems in terms of the charge perspective. So here we introduce the charge, then we move to electric field like this. And in case of here, the same similar problem is discussed in the alternate way. Like first we introduce the field distribution in terms of the electric flux density. And this can be used to calculate the charge density. So that is what nothing but Gauss law. So Gauss law is nothing but alternate another version of uh, the Coulomb's law. So in order to understand this concept very easily, if you see that some of the examples which we worked out for the Gauss law, like a line charge, infinite sheet charge, and then yeah, a spherical one. The spherical one, if you see that, it exactly looks that the field finally which is coming into the will exactly look like the that of Coulomb's laws expression. So they are actually one another same. So this tells about the charge distribution and the exerting electric field. So if you know the electric field, we can find the charge. And Coulomb's law tells about the opposite way. And they are having they are we can say that complement to each other. If the problem is complicated in Gauss law aspect, then you can move to Coulomb's law. And if you feel that Coulomb's law aspect is a little difficult, let's say if it is for concentric spheres or concentric circles or two parallel planes like that, then in that case you can go for Gauss law. It is up to you to decide that. Then we studied about the very important topic and which directly come into the application, that is the potential. So the definition of voltage, all these things comes here only. So the potential is nothing but the potential energy, which tells about in the presence of a particular electric field. When we move a point charge from a particular point, let's say from A to B, what about the work done? So that is what describes the potential energy with respect to the source charge. So that is what you easily describe the potential energy. Actually, here it's supposed to be small q, the small q which is moving here. So it's supposed to be test charge itself. And so and this initial conditions of the or the origin point of the charge, if we consider it is located at infinite point, then obviously the potential at this particular point VA will become zero. So this often refers reference point. So in it indirectly means that uh, when there is a electric field is available due to some charged body, the electric field is available. So from an infinite point, you are actually moving this point within the closed regions of the surface itself. So there comes the work done is coming to this. So that is nothing but the potential. So the potential or potential energy is nothing but the total work done by the charge. And always there will be a negative symbol will come. You could always see this negative symbol. So this indicate that the work done by a external body, not the charge itself. And if the electric field is opposite direction, this will become positive. So it indirectly means that this work done by the charge due to this attractive force of the electric field. So that is also interesting aspects. And next one, which we have seen, in fact, when we apply the concepts into the real field, uh, we first always supposed to calculate the potential gradient. So this potential gradient is nothing but the due to some electric field or flux D or E, whatever it is. So due to that, we can easily calculate the voltage at any particular point of X comma Y comma Z. And that is what we have seen. But if we know the potential, then we can calculate in the reverse way to calculate the uh, this E vector. So this is actually can be done with this simple. So this is integration. When we do that, differentiation automatically will come. But this simple, which we call this integral as an integral operator. So when this comes to this side, it will become differential operator. So these operators become easily exchangeable simply because we are assuming the entire region is made up of same material, which we call homogeneous. But if we have two different material, here epsilon r1, here it is epsilon r2, then this is a big question will come. So there are some additional variables will come into the picture that we will see in the maybe 2-3 units after we will see that. So such a things will be very interesting. So if you know the potential at any particular point, we can calculate the electric field. And very important thing you should know about that, this we already discussed about that, but more than that, if we have a flat surface and this flat surface has uniform potential, okay, so we let's say this is along the x direction. So Vx equal to V naught, let's say. So throughout that, it is going to be same potential. That is we call equipotential. And so if this is equipotential, then this particular inside, let's say there is a box or something, then it is full of electric potential is equal to zero. So that surface is often referred as equipotential surface. And this surface will not be having any field components because this differentiation with respect to dx is going to be zero then. So that is nothing but the electric field. So the electric field along the x-axis, or if it is a surface, then along the x and y axis in the plane, or even if it is a volume, then within the volume there is no field component. So that is what we can see here. So within this body, there is a uniform charge, and due to that, there is a uniform potential. And due to this uniform or equipotential, the electric field is zero. And this is what happening inside the conductor. So if you take a conductor, this conductor full of atoms, and these atoms are tightly binded, and their charges will be already available in the conduction band. So there will be about nearly about, let's say, 10 power 25 uh, electrons per centimeter cube, like that. This much density will be there. So this is everywhere it is available. So in that case, this is completely full of equipotential. And inside the any metallic conductor, we often take that electric field is equal to zero. So this is very important one we have to understand out of the potential. And we move to boundary value problem. And the boundary value problem is telling about if we do not know both the charge, okay, we do not know the charge and we do not know the electric field. So sorry, if we know this, we can calculate this, and if we know, we can calculate this. But if both do not know, then if we know only this potential at the boundary conditions, then we can calculate this both electric field as well as the field charge, both we can calculate. So that is what the important works carried out in the uh, just quite before Maxwell, during the times of Ohm, Gauss. So they have solved many of the electrostatics problems, and that is often referred as electrostatic boundary value problem. So this needs actually two important equations under the second derivatives of the potential, which we often refer as Poisson equation and Laplace equation. So this Poisson equation we have seen. So this comes with the charge. So these charges often referred as intentional charges, which means that because of, let's say, there are some charge distribution is available and it has this charge density, Berlin charge density or something. So, and this, when we apply this equation, then naturally this charge density is not equal to zero, and such a body supposed to be solved with Poisson equation. Let's say if you take semiconductor, here in this actually semiconductor is completely will be having its own charge density. Either it may be positive or negative, like N type or P type, like that. So there will be a charge density. But in case of dielectric material, the charge density will be equal to zero. And that is often referred as intentional charge density is equal to zero. Okay. So this, if it is equal to zero, then we will get the special condition called Laplace equation. And this Laplace equation has del square operator. This is often referred as Laplacian. So Laplacian of the potential. So like that we have to say. And like how we call here as a divergent of a potential or potential divergent, like that. And here we have to call this as the Laplacian of the potential. So when we solve the Laplacian of the potential of a given boundary value problem, we can easily calculate the potential. By the way, we can calculate the electric field, and by the way, we can calculate the charge. I already told what are the steps to be involved in this, and we also solved one simple problem, that if we take a one-dimensional problem, so here along the x direction, at x equal to 0, we have a one metallic structure or some conductor which is given with the potential of 0, like it is connected with some battery negative, like that. And after, at a distance of d, we have another electrode, and this electrode has potential of V naught. So this potential is V naught. So that is what indirectly it is given. Now we have to calculate the capacitance. So capacitance need Q by V. So for that we need this Q, and as well as potential also we should know everywhere else. Then only we can easily calculate the capacitance. So how to do that? And this is a dielectric material. There is no information about this charge density. Intentional charge density is not given. So why I am using this intentional? Because let's say this, let us take this same semiconductor problem itself. The semiconductor has some charge density in the semiconductor, but due to some material property, this charges may go inside the oxide. So then they deplete the oxide property. So that is a special case. but originally they don't have any charge. That is the idea. So that is the intentional and contentional like that. So intentionally, there is no charge density available here. So rho v equal to 0. So then the problem is very simple. We can easily solve with the uh, Laplacian or the Laplace equation we are going to take. And it is a one-dimensional problem. We can write like this. And we can solve this by one integration, and second integration we will get this. And so this we are going to apply the boundary at x equal to 0, at x equal to d, we are applying the boundary and we will get the potential equation. Since b equal to 0, there is no constant term like this comes. We got the potential, then we can follow this procedure. So this procedure, if you know that, then you can solve almost any problem. Then we can easily calculate the electric field. From electric field, we can calculate the density, that is field density. And this field density is absolutely equal to the charge density. This charge density when you integrate over the surface. And here the surface will be having this some area. So that is the surface. So that surface when you multiply, then you will get the total charge density. The total charge density in either of side, here in the positives or in the negative, here it is positive like that. So any one you can consider. So that charge density we can easily calculate. Since the charge density is calculated, you can simply divide by the expression V, then you will get that. You can easily get, sorry, the potential here, applied potential is V naught. And that gives us epsilon S D. Okay. In many of the books, you can see that this epsilon naught, sorry, C is nothing but epsilon naught A by D like that, this formula. Here A is the area, D is the thickness of the oxide. Here this problem is homogeneous problem, so it is very easy. But in case of some rare cases, you will see that there are two different materials will come, epsilon R1, epsilon R2. And in that case, the electric field here the electric field is E1, here the electric field is E2. Then both are not equal. If they are not equal, then solving this, and you can't apply this simple divergent problem directly. So we have to do some alternate method. So we will see in the future class how to do that. That actually will comes under boundary conditions. So this is boundary value problem that is called boundary conditions. We will see then. Yeah, the last class we have completed up to this, I think. So now we will move to the next other examples and some numerical examples also we will go. So how to solve this boundary value problem for other shapes. And we are going to derive once again the capacitance for a coaxial cylinders. So the coaxial cylinder is nothing but there are two cylinders. So there are two cylinder. They are having same axis. And so one is having radius of A, another one is having radius of B. And this middle one is going to be applied with the potential of V naught. And the outer one is simply grounded, which means it is having potential of 0. In that case, what about the total capacitance between these two? So like how this problem is a simple rectangle structure and this is a cylindrical structure. So how to solve that? It is very easy. We are going to take the Laplacian of the potential. So del square V equal to 0. So that is the Laplace equation. And so we are assuming there is a dielectric material in between that. So now this equation you have to take. So you have to take this equation. And in this, we are going to take these two terms as 0 because with respect to that, there is no change in the in terms of material property or anything. For example, here it is a conductor and dielectric and conductor like that it is coming. But in case of just around this direction, there is no change. Which in other words, we can say that it is a homogeneous. By the way, even if you differentiate, it is going to get it is going to get 0. So that is why we are not going to assume in this direction, only along the rho direction we are going to take. So this so this is reduced to this equal to 0. Then when you differentiate, anyway, this 1 by rho will become 0 again because of multiplying this. So this, when you do that, you will get like rho dv by rho dou equal to a, like that will come. And this rho, you can bring it to this side, so that you will get like this, dou rho by dou v by dou rho equal to a by this. And when you solve this, actually you will get this value will come. So I believe you can easily work in this way. So you can go here and you can go this way and apply boundary conditions. And when you do that, you will get this equation, potential equal to V naught natural logarithmic of. So in some books, you can see that it will be mentioned as log. So the difference between this two is this negative values, which how it is being applied here. So within the cylinder, the negative values are not possible. So anyway, you can use log as well as ln, both you can use, since all the values are positive. So here V equal to V naught ln of rho by B and ln of A by B, like that it has come. Now we are actually supposed to calculate the electric field. So the electric field is nothing but divergence of this. And since it is a one-dimensional problem with respect to rho, which will be nothing but minus dou V by dou rho. We already calculated this value. So it is already here. And only have to apply this negative sign. So when you apply the negative sign, this A by B will become B by A. That's all. And you are going to add a unit vector, which is a normal vector. Then you will get the electric field. Electric field, when you multiply with epsilon, the dielectric materials property, when you multiply, you will get the density. This density is equal to charge density. And this charge density you are going to integrate over the surface. So you are going to integrate over the surface, and you will get the surface is nothing but the length as well as this. So the total with respect to the rho, you are getting 2 pi a l. So by the way, you will get the q. This q you are going to divide with the v naught. So the v naught will be cancelled. You will get this. So this is one way of doing the work, starting with the Laplace equation and going this way. The same problem can be solved in the reverse way. First, we have to calculate the charge density. According to Gauss law, we know that it is nothing but integration of d into ds. So that is what it is written here, epsilon e ds vector. So when you do that, you will get this. And then by differentiating this, you will get the, so this e rho, if you take, then you will get this in terms of q divided by epsilon 2 pi rho l. So that is, you will get the electric field. Once you know the electric field, you can calculate that voltage. And in this way, when you work out, you will get this expression. So either of the way we can work. So in both the way, you can see that the voltage, or sorry, the potential term is same. So it is up to you to work on this. So, but this is a boundary value problem, and this is most probably this is a Gauss law solution. And we can apply the very similar workout for the coaxial the spheres. So if you apply for coaxial spheres, actually you will get this. So my best advice is just to work on this. So don't write like this like that. You have to work out in the proper mathematical workout. And even if it is a detailed derivation also, you have to prepare for that, because in the exam you can't expect the size of the problem. And anyway, we will give with respect to mark, but still then the way you are applying that. For example, when you do this way, it may be bit lengthy, and this way it is bit shorter. But however, these problems are not going to come for the exam. So you will be getting a completely new problem, and you can't expect the size. So always you have to practice in a detailed way. So even when you work for rough work, always do step-by-step work properly. If possible, give numbers, equation numbers, 1, 2, 3, like that, and substitute here and there, like all the things actually I will expect the answer. Once again, I am saying that electromagnetic field theory is more mathematical course rather than a physics course. And here is another example, which is very interesting example, that there are two semi-infinite conducting planes, which means that in one side it is having origin and it is going endless in the other direction. And here also that. And there is a gap between them at the origin with an infinitely small gap, which means the gap between them is almost nearly zero. And moreover, they are not touching each other. That is the key thing. And uh, and these two planes are located in two different angles. So one is along the phi equal to 0, that is along the x direction it is available. And phi at another one is at phi naught, which is nothing but pi by 6. So pi by 6 is nothing but 30 degree. And these these infinite conducting planes. So and they are actually they are given with two boundary conditions. Their potential is equal to 0 for this, and here it is V equal to 100 volt. Then the question is, what is the uh, potential everywhere in this between these two and the electric field, which is going from the high potential to low potential? Or what is the electric field? That is the question. So the problem can be easily solved. We can easily solve because there is no information about this material in between that. So we can assume it is a vacuum, and vacuum has the epsilon r value equal to 1. Therefore, the we can simply take it is epsilon naught. Then we can easily solve the boundary value problem. So first you have to take the Laplace equation and you have to reduce to the given problem supposed to be reduced with respect to one-dimensional or two-dimensional, whatever it is. And here you can see that the structure is varying with respect to phi, and with respect to height, that is z direction, and with respect to the rho direction. In all the other directions, it is simply same. It is an infinite sheet. In that case, there is no field component will be there. Or the field component will exist only along the phi direction. So you can easily always think that there will be a phi component alone will be available for the electric field. Just one simple understanding. So this become a one-dimensional problem. When we solve that, we will get this simple equation. And we have to calculate A and B. So for that, we have to apply this at phi equal to 0, at phi equal to pi by 6. What about the V value? So this equal to, first we will assume V naught, then we can, later we can substitute this equal to 100 volt. So you can get the value B equal to 0 comes, and here A become this. And this phi naught, actually, it is not substituted as pi by 6, it is given as phi naught itself. So that in later we can vary this value. So we got this potential and the electric field calculated. From that, we can calculate electric field at any particular point with respect to phi. So when you substitute 0, you will get 0. When you substitute pi equal to pi by 6, pi by 6 will become pi cancel 6 and 600. When you do that, you will get 100. So that problem solved. So that is the simple method. We can calculate electric and magnetic field. So this is how the structure look like. Along the x-axis, we have one infinite sheet, and at phi naught along the phi naught, we have another sheet. So this phi naught increases. We can see that particularly if you notice the electric field will always decrease. And if the rho value increases, the rho value is nothing but along this direction. So along this direction, when you move, the electric field will be strong here. The electric flux lines will be strong or dense here, but it will become loosened here. So that is the indirect meaning of this of this equation, which is the solution. Okay. This is how we have to work out the problem. But interestingly, if you notice the Laplace equation, it is a second order equation. So can anyone say what is meant by second order equation? Second order, it's a quadratic equation. So how many solutions will be there in a quadratic solution? Anybody knows? Mhm. Am I audible to you?
Sir, two.
Yes. So there are supposed to be two solutions in general for this kind of second order problem. Second order problem means that the variable which we supposed to solve will be having square. Here the operator has the square. Okay. So there's supposed to be two solutions in terms of the variation in the potential. That means the potential is supposed to be two different values. But so far now we have solved for only one value. So why this approach generally maintained in everywhere? Because of the uniqueness of the solution, which we call that as a unique, which often referred comes under the uniqueness of the electrostatic problem. So whenever, particularly in the homogeneous cases, that everywhere else, within this two region, within the boundary, you can take any boundary. So let's say there is a box. This is one boundary two. Within that, the material is same. We'll be having only one material, and charge density is also equal to zero. In that case, the problem become linear homogeneous. Okay, linear homogeneous. Therefore, the operator, the del operator, often refers linear differential operator. The linear differential operator will give only one solution. Uh, that is often solved with this uniqueness theorem. So this is true. This is one of the very important proof within the electromagnetic field theory to tell that the theory, what do you call, the theory acclaims that itself is correct, and that is one of the very important requirement for a particular theory to become complete. So which often refers completeness of a particular theory. For instance, uh, this quantum theory cannot prove itself, because when you take the particle problem, and it may end with it may sometimes end with the wave problem. The wave problem may end with this. So some duality will be there. So there should not be two solutions. Only one solution should be there for a given problem. That is what we call the uniqueness theorem, and this is one of the important indicator of a particular theory to be complete or not. So in case of the uniqueness theorem, that the all the boundary value problem within the electrostatic, here we are having only one field, that is the electric field. When the magnetic field comes, definitely there should be two solutions, because there will be two operators will come. So this boundary value problem will be having only one solution. That means the uniqueness will be there. And how to prove that? So assume that there are two solutions available for this Laplace equation, and we in the beginning we will assume these two are not equal, and at the boundary means at let's say x equal to 0, potential equal to 0, at x equal to t, potential equal to v naught. So at these boundaries, this when we substitute v1 or v2, both supposed to give the same value. So then in that case, the v1 and v2, when you substitute in the expression at the boundary condition, then it will satisfy this particular problem. So this is correct. And now, since they are actually completely different values or different solutions, then v1 minus v2, the difference actually we are finding, and this we call it as a difference, the potential difference. And when we calculate the potential difference, we will get this value. So this is nothing but del square v2 minus v1. And this operator is a linear operator. So we can simply apply the simple basic mathematical workout, that del square v2 minus del square v1. So this two values already they are 0 from this. So this difference, Laplacian of the difference, potential difference is also 0. And now we are going to assume vector, and this vector has v del vd, and there is no it looked like there is, why this is actually taken, because later actually we want this del operator, del square operator come into the picture. So first we have to check which mathematical identity has this del square v term. So the simple one is del dot vd dot del v. So this is the one will give that. So that is why this is actually taken as the a vector. Now we are going to take the dot product of that, and when you take the dot product with that, so when you take the divergence of that, then you will get this true operator. And this already we proved this value equal to 0. If this is equal to 0, then this del dot v equal to this. Okay, so therefore we got this equation, and this equation we are going to apply the divergence here. So that the divergence theorem says that if you do with respect to volume, you can make it as a closed surface integration. And by the way, you can remove the del operator and you will get this vector. So this is nothing but this A vector, which we already know that. And this, for this particular value, this already equal to 0. So this right hand side becomes 0, and therefore we can easily get this equation. And when we integrate this, we will get this solution because it is a simple dV alone available. So therefore, this is the value will come, and which is equal to 0. And therefore, del V is nothing but uh, this V2 minus V1, which is supposed to be equal to 0. In other words, V1 is equal to V2. So what actually this look like some kind of mathematical trick or something, but it look like trick because we are actually assuming a particular problem, and this if we take any other workout, this doesn't look will work out in that way. Okay, this particular problem is taken because we need a particular mathematical identity which will come with del square VD like that. So that is why this being taken. If you have some other working method, you can also do in that way. So what this uniqueness theorem says that within the boundary, if you get two solutions, let's say potential at this particular point and potential this particular point, and any particular point, there will be only one solution will be there, and depends on the value, depends on the corresponding locations, the value might be changing, but there will be only one electric field component. There is only one potential expression will be there for a given problem. There won't be any two plus or minus like that. Actually, we can't get here. That is nothing but the uniqueness theorem. So this is very, very important workout. And so this uniqueness theorem supposed to be checked in multiple cases. Even this supposed to be checked in the case of Gauss law as well as Coulomb's law as well. So in other words, we can say that at least within the scope of the electrostatics and magnetostatics, and if there is only one field component available, then uniqueness theorem applies. Now we are actually going to another alternate method, which we call images. We already know that if there is a perfect conductor, or simply if we assume there is a conductor, then it is having equipotential. So V along the x comma y comma z within the boundary of the conductor, if it is constant, then the electric field is equal to 0. So within the perfect conductor or within a uniform conductor, always we will be having electric field equal to 0. Okay. So this is the, and therefore their surface potential is constant. And in case of perfect conductor, if it is given with 0 potential, then that is often referred as ground plane. This will be grounded. And in this particular situation, we are going to keep one particular charge at a particular height from this equipotential surface with V equal to 0. So a ground potential is kept along the y direction. In the y-axis or y-axis plane, and at a height h, we are actually going to keep the. Yeah, you can ask any question. Somebody raised the hand, so you can ask question. Okay. If you have any question, immediately you just ask the question, whatever that you have any questions regarding the workout or anything. Even in the offline also you can ask, no issues. Okay, so now we are going to take a particular problem that there is a charge, and this charge of any particular shape is located at a height h from the equipotential surface with potential equal to 0. So throughout that everywhere the potential equal to 0. And so in order to calculate the electric field at any particular point in the presence of this such a perfect conductor with the ground plane. So then how we can calculate electric field at any particular point? And we can't simply account this alone because there is a potential distribution of something else is available, this ground plane, or you can call it as a equipotential surface or whatever it is. So some reference plane is available with potential equal to zero at a finite height or at a finite distance from the surface. A particular point charge or particular shape of body, charged body is available. In that case, the electric field, you can't simply apply the Coulomb's law or Gauss law directly. Then it is this problem look like very tricky. And in the even with the homogeneous case itself, the boundary value problem is very difficult because here you have only one boundary. There is no any other boundary or anything else is available. So we can't solve with Coulomb's law or not even with Gauss law and not even with the boundary value problem. So it looked like very difficult to solve. So for that, there is an alternate solution has been given. That is what we often refer as the images or popularly known as method of images. So what this idea of method of images tells here is if we have a potential V equal to 0 at this particular line, and from this at a particular height h, we have a charged body. Okay, this charged body has, let's say, this is positive charge. Now we already know that the electric field due to this point charge towards this particular direction, let's say this is E, and because of the E, there is a potential available at this particular point. And solely because of this point charge, the electric field cannot become zero or the potential cannot become zero. And how this potential can become zero if we apply some little some novel method. So what people have tried is if we put exactly at the depth of h, if we have a negative charge, then this electric field and this electric field vectorially cancel each other and we will get the electric field. And this is also same for any particular point from here. So assume that from here we have distance of r1 and here also we have a distance of r1. So both are same. Their angles also same. Therefore, this component will be having the electric field will be like this direction and this electric field will be like this direction. So the net electric field is supposed to be vectorially same, so which is quite same as that of here. But the electric field, the potentially will become definitely zero at this particular place. So that is what the indirect meaning out of here. So this is the this is what bring us the solution. So in other words, if you have a equipotential or a potential equal to zero over a uniform surface or a uniform line, and just above that if you keep a particular charged body and its exact opposite charged body will be with the same shape. So if you have triangle here, then you will get exactly image of the triangle will be there in the bottom, and which correspondingly cancel the electric field and make this surface potential, and which is same as that of the initial condition. Or before this also it is same, V equal to 0. After bringing the charge also it becomes 0. Then there's supposed to be an image charge supposed to be available in the bottom. It is like how we see in a mirror. So when we see in the mirror, there is no person available here. Okay, but it looked like an image with respect to the electric field, which is the photon what we see. So we see ourselves in the depth of here. And you know about the properties of image, exactly it is opposite to that. So you can see that is why whenever you draw the image charges, you're supposed to draw the shapes properly. And this give an idea that it can be applied to many numerical problems wherever this surface potential is coming. Here it is, we are taking as a 0. In some places we will be having the potential everywhere become uniform surface. In that case also we can apply the very similar property, because since this is equal to equipotential, then electric field definitely is going to be 0. And in that particular situation also we can use this here, this method, and which often referred as method of images. This actually developed by Lord Kelvin. So you know about that, the Kelvin's important works, including the battery and all the way. And he has come up with this brilliant idea of explaining the things. And This is actually very rare event of having equipotential surface very close to the charged body, and there comes the electric field and the potential everywhere else, and the calculation of work done and the flux density, all these calculations uh, is a very rare event. But in recent times, we can see that in many applications, you can see such a behavior. And using this particular method of, or in other words, the method of images, we can solve many problems. So how to handle this? Whenever you have a particular charged body and there is a particular surface, and the surface has uh, uniform potential throughout the plane. And if it is a zigzag, we can't assume as a uniform one, because along with respect to the x or some other direction, there is a potential difference will come. So with respect to the locations, for example, if it is a zigzag one, this height is different, this height is different. So we can't apply this one. So there should be one single condition. There should be a uniform surface, and just above the surface, we should have some charged body. It may be positive or negative, whatever it is. Then you can remove this and you can place exactly on the opposite side. You can place one opposite charge. Then you can calculate electric field due to this charged body, due to this charged body, and you can easily calculate the electric field. Once you calculate the electric field, you can calculate potential everywhere else, and then you can calculate work done, and you can calculate capacitance. So many problems we can solve within the scope of the electrostatics. So if you carefully see that from the beginning, and that Coulomb's law, and then Gauss law, and then potential gradient, and that way we have this Laplace equations all the way. They are actually, we can say that they are complement of each other. Whenever one problem you can't solve, we can use, let's say, if you can't solve with Gauss law, you can solve with Coulomb's law, vice versa again. Then if both cannot be applied, then you can try to apply boundary value problem. Within the boundary value problem, some special case that if there is a equipotential surface comes, then you need not to worry about that. Simply you can replace with the image charge. And but what are the things you should be very careful at what height it is available, at that depth you have to keep it. Otherwise the problem will be collapsed. And this Lord Kelvin himself solved this problem with the idea of electrostatics itself. And so here we have a surface and we have a positive charge. And according to the theory of images, or the method of images, we are going to keep the same depth, we are going to keep the negative charge. And we supposed to calculate the electric field due to this particular point P. And this point P is located at a distance of r1 from the positive charge and or the source charge, and this r2 distance from the image charge. Okay, now we have to calculate the electric field at this particular point. So we can easily say that it is positive, so electric field will be like this, and it will be repelling like that, and because of that it will be like this. So there will be electric field along this direction sometimes. So this vectorial addition is very important. So we have calculated the electric field due to the positive charge and the image charge, and then this is the value. So you should be very careful about the R1 and R2 representation. And with respect to the this plane origin, if we consider, then we have to calculate the R1 and R2. So since it is located at x comma y comma z, then we have to triangulate this problem with proper trigonometry. So we will get R1 and R2. Once the R1 and R2 has come, then we can calculate the corresponding vectors with respect to the origin. And when we find the difference, we will get R1 and R2 here. So then we have to substitute here. Then we will get the electric field. So this is the electric field due to everywhere in presence of a equipotential surface uh, with respect to the charged body. Okay, so if this charged body is moving anywhere else, depends on the height h, then automatically this will change and the electric field also will change. And if we say that if it is h equal to 0, then you will get this H equal to 0, then this problem simply will collapse and will reduce to uh, uh, this this length equal to this length will come, so both will cancel each other, then the electric field will become 0. That is what we expected here. And we can also, since the electric field is available everywhere, we can calculate the potential as well. Now, in order to prove this concept is correct, we can take at the boundary. The boundary is only one boundary we have, that is at z equal to 0. We have this v equal to 0. Okay, that or v equal to v naught everywhere. So that both are almost same. So now what we are actually going to take is, if this is actually a uniformly charged body, then it will be exerting its electric field in the perpendicular direction, which even we have seen here that always the electric field will be perpendicular in this direction or in this direction. Okay, so in other words, so you can also see here the electric field always will be perpendicular, at least perpendicular to the equipotential surface, and therefore we can easily apply the Gauss law, and the Gauss law tells that uh, the the field density, the field sorry the flux density, which is nothing but epsilon E, will be is nothing but the charge density. When you integrate over that, you will get the total charge will come. Okay. So this total charge, now it is divided with respect to this height and all the way. By the way, we can define the electric field, and when we integrate it, we will get the total charge. And this, when you do this workout, this is all available in study Q. You can work out anytime, you will get this negative value. Okay, so interestingly, there is a equipotential surface of 0 or V naught. This is a equipotential surface, uniform one. At a particular height h, we have a positive charge, and now we are calculating the electric field at any particular point. Now at this boundary, when we try to calculate the potential, then we will see that at the height of minus h, okay, then we have a negative charge. So that is what it is indirectly calculated here. So this theory proves itself is correct, then method of images is a valid approach. And which here also the uniqueness theorem will come into the picture and will say that same. So they in fact in reality, under this there should not be any potential, but here also if there is a potential available, then we can easily calculate out of that. And there are so many applications for the method of images. Wherever there is a symmetry is coming into the picture, then we can apply there. For instance, most often cases, the monopole antenna. Okay, so what is monopole antenna is nothing but we are going to have a ground plane. We need not worry about that. It is simply a metallic plate. Okay, and in a metallic plate, I already told that there will be a uniform charge density. If there is a uniform charge density, obviously the potential is going to be 0 or uniform. Therefore, it becomes equipotential. I will mention this is the equipotential surface, and this equipotential surface, above that we are keeping one line charge. Then its corresponding line charge will be available here. So this is a simple dipole problem, positive, negative. And because of the line charge at any particular point, we know the electric field, that is E1. Because of this negative direction, we have the electric field. Both, if we add each other vectorially, then we will get the resulting electric field. And interestingly, this, with respect to this equipotential surface, all these electric field will be available in this particular direction, not in the below direction, because in the below there is no real charge or no field component will come out of that. That is the interesting thing. And if you solve with the simulator, you will get this kind of picture. So this is the equipotential surface, and in the center we are going to keep the vertical structure with a height. Okay, this height is very important. Directly if you touch that, then there is no meaning for that. So this is the one. And where we can alternatively work, let's say you have a structure, let's say one structure is like this and another structure is like this, and you have a coaxial cable. The coaxial cable positive is connected to this, the negative is connected to this. Now we are going to calculate the electric field induced by this two charged body, and you can see that if we draw a line of symmetry, both look same, but this is positive, this is negative. So we can solve the problem with two structure like this, and we can calculate the electric field. Otherwise, applying the method of images, we can simply remove the structure, and if we apply the method of images, then we can easily calculate the electric field everywhere else. That is also we can do that. This is why in the some of the very tricky simulations, people use this line of symmetry. And let's say I have to solve for a particular problem like this. Okay, so this is carrying a current, and I have to calculate the electric field due to this plate. So what people used to do is they will put a line of symmetry, and this line of symmetry they will call this the equipotential, or simply they will keep this equal to 0. Then this simply solve the this simply give the corresponding the charge distributions, whatever it is. It will take the image of it and it will calculate it. So we can reduce the computational burdens into half because of that. So in the even many of the simulator do this naturally by identifying itself a symmetric structure. So this is the important application of method of images. Anyway, doing mathematical workout is simply tricky, so I'm not going to ask any questions, any numerical questions, but there will be some theoretical aspects will come in terms of explaining what this images and what is the advantage of method of images. So for that you have to go through the book properly, and this how to prove that particular charged body. Here it is given proved with the point charge. If the same derivation asked for some other structures like line charge or a volume charge or a surface charge, how we can work out. So that is, you can easily figure out, but the problem is a little bit tricky, so you have to think about that. And this is very recent times, this monopole is used in multiple places. So this is car antenna, and this car antenna works with the same principle. Receives the signal because of this metallic structure which is in the bottom. If this metallic structure is not available, this antenna will not work at all. And this is many people you know about that, this shark antenna. The shark antenna has an active region here which will amplify the signal and will take the radio signal to the receiver, which we call radio, and this is the antenna. Okay, so this antenna is simply in the equipotential surface above a particular height. They kept like this. So you can keep any shape. Here it is given with like this shape, and this type of shape is indirectly to reduce the total length of this wire. So if you keep as a vertical one, and if you keep like this, there is no big difference. Both are going to operate at same frequency. So this is the advantage of the shark antenna. And you know about that Bluetooth dongle, which look like this, such a very compact one, and inside that, so here you can see that up to this you have this metallic base, and after that a small region will be opened. So that is this region, which is a monopole antenna. So here the connection you can see here, this connection is taken here, and they made a bend. This is the very same bend they have done it here. So instead of keeping like this vertical way, we can bend it all the way. I'm sorry I have taken too much of time. You can leave the class at once and go to the next class if you want. So I believe you have understood. In the next class we will go to the next problem, and particularly I am going to solve many numerical problems considering the quiz on 25th. If you have any questions, you can ask now. If you have class, please leave the